So welcome to the second RISIS Research Seminar of this year, where we have another interesting presentation. At the beginning, maybe a brief reminder that the RISIS datasets portal and the facilities are still open. You will also get news about the upcoming RISIS Association that will be announced in this year soon. And the RISIS seminars will stay a vital element of open discussion on interesting ongoing research works in science, innovation, policy studies. And also today we have a very interesting presentation by Joseph Alexander Emmens from the Universitat Autònoma de Barcelona. And he will tell us about his work on teams and text collaborative innovation in the knowledge space. And we are happy to have a distinguished discussant, Ernest Miguelez from the University of Barcelona. So Joseph, the floor is yours. As always, we will have a presentation of about 30 minutes. Then Ernest will step in as a discussant. Then we can have an open discussion among the participants.
Perfect. Okay, thank you so much. Thank you for the kind introduction. We checked it, so I think everything is good with the slides. And
yes,
thank you, Ernest, for preparing the discussion. I'm looking forward to it. It's great to join a real science and innovation focused group. So I'm looking forward to the discussion. This is actually my job market paper that I've just finished, or I'm finishing up on the job market. So I'm excited to get to talk about it with you all. And let's just jump into the paper. So we all know here, especially, that innovation is very important, right? Innovation drives productivity, solves our biggest challenges. But we also know that inventors work best in teams. And the literature showing this argues that the rise in the dominance of teamwork is in part due to an increasing knowledge stock. So the idea being that over time, knowledge accumulates, the innovation frontier expands, and presents problems too complex to solve alone. So in this paper, I ask, what's the impact of this increasing knowledge stock on team innovations? Where specifically, I ask, does the quantity of previous innovations that a team is building on determine whether their next patent is a breakthrough or not? Okay, so a breakthrough I define as an innovation that is both new and impactful, where the compound definition is key. You might be very novel if you create a 5-legged chair, but I measure impact as people building on your work. So if nobody builds on your work, you haven't started a new and successful research field. Therefore, it's not a breakthrough innovation. I then go down to the micro level and ask, how can a team increase the chances that their patent becomes a breakthrough? So today we're talking about innovation. But here, especially, we're interested in academia and science in general, and there's a strong parallel to academia. You could describe all economists and econ papers as some combination of theory and empirics. Okay, you'll have pure theory profiles, pure empirical profiles, and then some will be a combination of both. And consider this famous case of collaboration that helps exemplify. Milton Friedman collaborated with Anna Schwartz to write a monetary history of the United States. And now, a monetary history was a truly seminal breakthrough piece of work in the monetary literature, partly because of its contribution to the role of money, but also through its combination of theory and empirics. But the problem is, if you were to read a monetary history and you knew nothing else about Friedman, Schwartz, or the field, you would struggle to disentangle that Friedman came from a more theoretical background and Schwartz did more of the empirical. That's why, in the first step of this paper, I present a novel model of collaboration that can disentangle the knowledge contribution of each team member to team output. This is going to allow me to locate the team, or in this case, as Friedman and Schwartz, as different points on this line in this space, also represent the work that they produced. Okay, so I've put a monetary history as some combination of both in the middle. And therefore, I'm going to build up what I call a map of innovation by locating inventors, teams, and patents, or in this case, economists and econ papers, as points in this space. And by using it spatially, I'm going to define measures to answer the research question. Okay, so for example, was a monetary history of the United States novel? It was. It wasn't so common to combine theory and empirics, and we could observe that there weren't many similar combinations of knowledge in the field before. However, now, naturally, it's a very common method of doing economic analysis. So you would see this over time being a more common combination of knowledge. And also the team, we can look at their little section of this simple case, this line, and examine, is there a lot of previous work in that space combining knowledge in the same way or not? Okay, so by building this map of innovation, I'm going to answer the research question on the effect of previous innovations on a team's chances of a breakthrough. And I do that through a two-step procedure. In the first, I represent the latent inventor and patent knowledge. And I do this by modeling collaboration directly through the lens of a Bayesian model of natural language processing. Okay, so this model is the first, to my knowledge, to disentangle the individual contribution to the team knowledge output. Okay, so when applied to high-dimensional patent text data, it allows me to build this map of inventors, teams, patents, and research fields called the knowledge space. Okay? In this simple example, the line connecting theory and empirics, this is the knowledge space. And I can locate Milton Friedman and Anna Schwartz's points on that line using this model of collaboration. And this defines the boundaries of innovation. And then I take snapshots of it at different points in time to define two important measures. The first are breakthrough patents. Those are patents which are invented in research fields with little or no previous innovations, but which go on to become vibrant research fields. Then the second are a team knowledge field. This is a representation of the team in data, which corresponds to the set of research fields available to the team. Now, in the context of the line, a breakthrough patent would be a point on the line, for example, monetary history, where very few previous patents or papers existed with a similar combination, which many future pieces of work combine knowledge in the same way to build on that area. And the team knowledge field, in this case, would be the section of the line spanned by the team. Okay, so the line between Friedman and Schwartz. The model then says if the team overlap with an existing innovation, there's some combination of them that they can build on that research field. Therefore, I can count how much prior work and previous innovations was the team building up. So to be clear in terms of a definition, I'm going to use the term prior work to refer to the stock of knowledge in a given research area, like a point on this line, not that of a team or an individual. So having built up and populated this space, I then answer the research question using a continuous treatment reduced form model, where teams each build on different quantities of previous innovations. And I'm going to use premature inventor deaths as a random shock to the team knowledge field, where following the death, the set of research fields available to the team is going to change. Okay, and the first thing I show is that the knowledge content of a team's patent changes after removing an inventor. So the team is shifted into new research fields. And I use this to estimate the effect of the team pivoting to more or less advanced research fields on the chances that their innovations create breakthrough and spark new and successful research fields. So to give you a quick summary of the results, and then we'll go through them throughout the remainder, I show two new stylized facts thanks to this framework. The first is that prior work supports breakthrough innovations by increasing impact, but reduces novelty and therefore stifles breakthroughs. Okay, so the idea is there's a trade-off, a tension between two forces. One, each previous innovation represents a step up the ladder of development. Okay, this is quality work, typical endogenous growth theory argument that future patents can incorporate and increase their impact. However, naturally, when building on more and more in previous innovations, it's harder for you to be novel. So this tension I show through an inverted U shape between the quantity of previous innovations a patent is building on and the probability that that patent sparks a breakthrough. If you combine this with a second fact, which is that over time, teams are building on more and more prior work, and I show this by their team knowledge field, so their section of the line being increasingly dense and crowded with previous innovations. This, I argue, is a micro-representation of Nick Bloom and co-authors' classic idea that breakthrough ideas are getting harder and harder to find. And it means that teams are increasingly on the downward slope of this inverted U shape. They're building on a lot of prior work, and this also reflects the burden of knowledge idea. But these two facts together combine to explain the first empirical result. And that is that on average, decreasing the quantity of previous innovations that a team is building on following a death increases the chances that their patent becomes a breakthrough. Okay, so the idea is by reducing the quantity of previous innovations, shifting the team into less explored areas of the knowledge space, they're producing more breakthroughs. Now, it's quite an intuitive result, but it does not mean, using the simple aggregate result, that team managers should go on a quest for novelty or simply remove team members from the most established fields, because this is being driven by the fact that on average, teams are on this downward slope. But when you split it up, you see significant heterogeneity. And for teams that are building on advanced research areas, those building on a lot of previous innovations, it's true. Reducing the quantity of previous innovations they're building on increases the chances of them having a breakthrough. And I show that these teams are able to be more novel and introduce more new words. However, for teams in early stage research areas, the same change, so reducing the quantity of previous innovations they're building on, reduces their chances of a breakthrough. Why? I'm going to show supportive evidence that they're in fact on the increasing slope of this inverted U shape. Okay, they would actually do better by incorporating more established knowledge. So this does point to alternative policy outcomes that I'll discuss at the end of the presentation, but the idea is straightforward. R&D funding should be exploratory and be pushing into new spaces, but this paper argues that there's a limit to how far you can go if you care about breakthroughs. We care about breakthroughs precisely because they are new and successful research fields. So they can either drive growth or present new solutions to classic problems on health, climate change, employment, etc. And therefore, there's a limit to how far, R&D funding can go, and potentially cross-field collaboration could be a workaround. By combining inventors from established fields with those from early stage research areas, we can see a driving of breakthroughs in the economy by combining this novel perspective to well-known information. So I'll get back to the policy at the end, but for now it's just a preview. So given that this is a paper about prior work, it would be remiss not to mention my own. Now, I'm contributing to a number of literatures, one in innovation and the others more in teams. Here I'm focusing a bit more on the teams, where I'm obviously talking to the team characteristics and breakthrough innovations literature, where I'm highlighting my contribution in blue. And I argue that this framework and this team knowledge field that can be described along many dimensions is a unifying framework for studying collaborative innovation by replicating a set of well-known results from literature. Then clearly, I'm sitting in the team knowledge production and identifying individual contributions literatures, where my goal is to move this fantastic literature, which studies quantity or quality, into the direction of innovation. And I do this by leveraging this high-dimensional patent data text. Okay? So instead of categorizing inventors as low or high quality, I can describe the knowledge contribution of each team member, the theory or the empirics, and also capture and explain breakthroughs in the same space, allowing me to study the key producers of innovation, the teams. Which also then links to the final point, which is text analysis in economics, where it's important to mention two papers cited here, Carvalho et al. 21 and Theodoridis et al. 22, who use a similar topic model, a text analysis model at the patent level, but they don't have a production concept, a team production concept. Therefore, by introducing teams, I argue that this is a key paper to study policy and the production of future innovation. Okay, so I'm building on my own set of prior innovations that are great. So that was a quick summary. Now we'll go into the two steps, as I said. In the first one, I'll talk about data and the model of collaboration. And then in the second, I'll plug this into a much more standard empirical strategy. Okay, so we'll jump on. So data. In terms of data, my data are largely patents. Okay, I do merge in other information on other information for mechanisms or robustness. But one of the beauties of the natural language processing is that I get a lot of information which is latent in one source. Okay, so for anyone unfamiliar, a patent is very similar to a paper. You will have a title. This case is an engine start-stop strategy. Here we have the four inventors, Kalon, Kalinsky, Liu, and Swales, who wrote that patent. And then the owner of the patent, the assignee, in this case, and most often a firm. And then I've also shown you at the bottom the abstract. in the paper, I use the full text description, but you get the idea from the abstract, where if you were to read this, you would very quickly tell that this is an automatic engine, something from a self-driving car, because it says the automatic operation of a vehicle comprising an engine that can start and stop itself, etc. It'd be an easy task. And I'm going to use this paper throughout the presentation to demonstrate what I'm doing. But obviously in the paper, I use many more. So I trained the model on over 400,000 US patent texts, where I'm going to explain train and fit in a second. And once I've trained it, I fit it to over 2.2 million US patents. So this is simply to say, I'm going to have a very global measure of the knowledge space, where these 2.2 are drawn using stratified sampling on technology classes to get an idea of the global knowledge space, where later the treatment sample using these inventor deaths is going to be much, much smaller, but I can capture their position within this global knowledge space, where I observe the patent text and the unique inventor IDs. Okay, this is also going to foreshadow something many of you will be possibly thinking is, I need to observe the same inventor across many patents, similar to a team switcher in a fixed effect idea, to be able to disentangle their contribution to that patent. But I'll come back to this. So the first thing is I pre-process patent P into an object DP. DP is the collection of words that describe the innovation, and I argue that that reflects the knowledge contained, where I'm simply extracting all the informative words and dropping the uninformative words such as and, he, she, it, etc. So this object DP will describe the innovation. I'm now going to present a model of collaboration for that DP, which I model through natural language processing. So a team tau, which is a collection of inventors, produces DP together. I'm going to represent the knowledge in DP, and for each inventor I in a team tau as a combination of knowledge classes. In the simple example we had before, there were 2 knowledge classes, theory and empirics. And in the paper, I use many more. So I use 50, where I model collaboration directly through the lens of an author-topic model. So an author-topic model is a topic model, which is a model of latent Dirichlet allocation for anyone familiar. It's a very standard classic model of text analysis, where authors simply introduce who created and who produced that text. As the ATM, as I'll refer to it, proposes a model of how authors produce a text, where for me, authors are inventors, texts are patents, reflecting the innovation, and topics are knowledge classes. Okay, so a knowledge class is an area of scientific expertise. Okay, it could be theoretical or empirical economics. And intuitively, the ATM uses the co-occurrence of words and inventors across many patents to back out the set of latent but important parameters. Okay, so the first of these is the knowledge classes themselves. As a researcher, you choose the number. So K could be 2, theory and empirics. I choose 50. And then it's essentially a word clustering, where words are clustered on the probability you use that word when describing that class. Okay, so the idea is straightforward. If the model observes the words regression, discontinuity, diff in diff, standard error, etc., appear together over many patents, it will start to form one empirical class. And if it observes theoretical and axiomatic analytical proof appear together over many others, it will form a second class. And then for each patent and inventor, they have a knowledge profile, which is represented in theta. This is essentially a distribution across these classes. It's, do you have all your knowledge in one? Are you a pure theorist, a pure empiricist, or some combination? Where if a patent uses more words from one of these groups than the other, their weight will start to increase. And the same goes for an inventor. If they appear on many patents using words from one of those classes, their weight will start to increase as well. So the key point here is I'm locating patents and inventors as points in the same space through this theta I and theta p. Okay, let me give you a real example, which will be a bit more, easy to get to grips with. So remember from before, we had our engine start-stop strategy. Okay, this automatic engine patent. Now, we know that this is some kind of engine that can start and stop itself. And on the right, I'm showing you the top 4 of 50 knowledge classes for this patent's theta p. Okay, so what I mean is the 4 classes with the largest weight, and these sum to about 75%. So it's the majority. And the word cloud, they are the knowledge class. Okay, so remember, knowledge class is a collection of words where they're clustered on the probability you'll use that word. So that's why the size of the word is weighted by the probability you'll use it when describing that class. So I've given them the names above, as it's just a bit easier to interpret. So we've got, for example, that this patent uses 38% of its knowledge on vehicles, 20% on engines, 9% on computing, and 7% on automation. So the model does a very nice job of reflecting that this is an automatic engine. But it can go one step further, and this is the beauty of this simple model, is that I can show that Cologne, Kolinsky, and Swales hold their knowledge on the top 2 classes, and Liu holds their knowledge on the bottom 2. Okay, so it can disentangle the knowledge contribution of each team member. And how does it do this? If you look at Cologne, Kolinsky, and Swales, they have many other patents on vehicles, engines, cars, transport related, and they don't have stuff on automation. Whereas Liu has other patents on electronics and engineering, but doesn't have anything else on vehicles. So when they come together, the model says, probably Liu contributed the automation knowledge and the others the vehicles. So therefore, it's able to disentangle them as a function of their history. The important thing is that I'm locating inventors and patents as points in the same space. Okay, if you remember that line before, as points on the line, this is building up this map of innovation that I can later use to answer the research question. So I would like to show you it, but unfortunately 50 dimensions is too high, or it's hard for us to conceptualize. So I'm going to squash the 50 dimensions down into 2 dimensions. But just to be clear, that's only for the presentation. In the paper, I use in the higher dimensional space, but for now, it's easier for us to show in 2 dimensions. So I represent the 50 dimensional space in 2 using a form of principal component analysis. Okay, so by squashing it down, I can plot a patents research field, where a patents research field is an area of radius r around a patents knowledge profile theta p. So we've got below the same patent from before. This is real data taken from the space, where the red dot is our example automatic engine patent. And then the black dotted ring is the research field. The blue dots are other patents which belong to that patents research field, where, given that we've squashed it down into 2 dimensions, we still keep distance relatively constant. So by patents being close, they have a similar combination of knowledge, similar background. And you can take a snapshot of this space, which is fixed at different points in time, to measure the evolution of a research field. Okay, so in 2002, when this patent was produced, there were like 9 other patents in that field. But if you look forward in the future, for example, in 2019, there were more. Okay, it's 17 years in the future. More patents have arrived and built on that area. And this is the idea, to fix the space and then take snapshots over time to measure what I'm interested in. Okay, so this is going to allow me to define 2 new empirical measures. Okay, breakthrough patents and a concept of the team that I can then use in the empirical strategy, which allow me to answer the research question on what's the effect of previous innovations on a team's ability to produce a new breakthrough. Okay, so having built the space, I can now define these 2 measures. So the first is, by simply counting the number of patents in the research field, like in that simple example, I'm going to define a breakthrough score. Okay, so for here, the breakthrough score for a given patent P is given by, for each patent which is produced in year T, at some year in the future, S, you get a breakthrough score by finding the ratio between the post count, which is the number of patents which belong to that research field at that year in the future. In the previous example, it was like 70, and then divide that by the prior count. How many existed at the year it was produced? Okay, again, it was like 9. So then plus post. So this very simple function is essentially finding a ratio between what comes after you to what came before you. Right? So the 2 examples below give a clear example of the differences. And this is again from the same data set that are in the paper. So here I'm showing you 2 patents there is the blue patent, which is a manure spreader, some kind of farming object. And the green patent is an object browsing app. So this is for surfing the web. On the x-axis, we have the year. And on the y-axis, you have the total number of patents in that research field at that time. So the fact that the red line and the blue line and the green line intersect is showing us that both patents were patented in the same year. Okay, so both came in 2000. They were patented in different areas of the knowledge space, but they were building on essentially the same amount of prior work. Prior count was more or less the same, and because they intersect. That's how you can see that. However, post count was vastly different in both fields. The blue field didn't develop further. No one combined knowledge onto that space. And the green one exploded into a very vibrant research field, right? So the green one I classify as a breakthrough, whereas the blue one I don't. Now, I'm not saying that the blue one doesn't have value. Yeah? They may have perfected the manure spreader, but it did not spark a new research field. That's the idea here. So I'm going to try and explain which teams are creating these green patents, the ones that really spark future research. And so I define the team in a very similar way, where I define the team span as the set of all linear combinations of team member profiles. And then I extend this into k dimensions by radius r. Right? So the reason I extend it is this allows me to compare teams of different sizes, and therefore count this object n tau of t, which is essentially the number of patents within a team's field at any given time. Okay, so consider the example. Let's say we have one team, ABC, 3 inventors, made up of theta A, theta B, theta C. The blue triangle is the span, and then the red triangle marks the team knowledge field. You can then count the number of black dots, which reflect existing patents within that team's knowledge field. So for example, the team on the left is building on 1, 2, 3, 4, 5, 6 patents. Whereas if you remove C, suddenly the team on the left shifts and becomes the team on the right, and they're building on only 2. So teams are building on different amounts of prior work, previous innovations, but also inventors are contributing differently to the team. And the research question, if you remember, is what's the effect of the quantity of previous innovations a team is building on their chances of their patent being a breakthrough? Well, we could use this n tau of t, this count. However, I'm going to define an exogenous shock to this n tau of t to get a more rigorous solution. And to do that, I use premature inventor deaths. So I define a premature death as an inventor dying within 3 years of having patented. So it's a definition based on them being active, where 3 years is because that's the average length of time between successive patents for one team. And I identify this through the Kaltenberg and et al. Data. And then for a given team, if you remember, was denoted tau, define tau sub 1 as the team before the death, including inventor I, and tau sub 2 as the team after the death. Now, this is where they've replaced I with J or with no one. This allows me to observe the team over time and define a continuous treatment, which is this dose, D, which is essentially the difference between the quantity of previous innovations the team was building on, including I, minus what they're now building on after having shifted in knowledge space. So for example, the example before, which was ABC, we're building on 6, then C unfortunately passes away. Let's say that they are not replaced with another inventor. Then they become team AB. So they're building on 2. 6 minus 2 is equal to 4. So the treatment dose is increasing in the quantity of patents removed, right? So I don't allow for the team to replace the inventor with more than one person. So I'm only allowing for small changes where, full transparency, the choice to replace or not is not an exogenous shock. The death is reasonably exogenous. However, the other one requires a much more careful model of the supply of inventor knowledge, and it's something we can talk about maybe in the discussion. So now I have my X and my Y, and the rest is a much more standard outcome. I'm going to run the model on 582 treated teams and 1,709 controls, where a control never adds or removes a team member. And the model is run on a team times patent panel. So the idea is that each period, I observe a team for their first, second, third, or their ordinal patents, and I explain the probability that each patent S from team tau is a breakthrough with a conditional logic model, where the outcome is a binary indicator for the team being in the top 25% of this function that you see here, showing from before, the ratio of what came after to what came before. And I'm going to explain the probability that it's a breakthrough given a set of observables. Now, these are team and period fixed effects. These are high dimensional. So this is why I need a conditional logic model. A year fixed effect, given that patents are right coded, you need to control for the year, given that patents produced in 2024 haven't had time to become breakthroughs. So conditional on this set of fixed effects, I introduce the variables of interest, where the key ones are the quantity of previous innovations that the team was building on before the death and the treatment dose. Okay, so if you remember in the example, the dose was 4. Now, we need to control for how much prior work was the team building on before the death, given it matters whether you're removing 4 from a team building on 6 or 60, where beta 2 then is the coefficient we're interested in. What's the effect of shifting the team into a less explored area of the knowledge space with less previous innovations on which to build? Where then I control for the volume of the team span and also a set of other important controls. Now, these are for different reasons that we can talk about maybe when we get to the results, but the idea is the death will potentially shock other team composition factors. For example, the gender diversity, age, experience diversity, race diversity, and this would be an important control. But also the size of the firm employing the team, as in the number of inventors, as this is one way to start to get at the potential confounder of which teams can replace these dead inventors and which not. Okay, so we can talk about that a little bit later, but they're there more for an identification concern. So let's jump into the results for the last few minutes. So if I was to show you this figure with prior count on the x-axis and the probability of a breakthrough on the y, where this is at the patent level. So this is the patent research field level, the circle we drew. What shape would you expect it to have? Given that prior count is in the x-axis, sorry, in the denominator, you would expect it to be downward sloping. However, that's why it's interesting. We see this upward sloping region and this inverted U shape. Now, this is driven by the fact that a breakthrough requires both novelty and impact. And prior count, which is the quantity of previous innovations, introduces this tension I described earlier, where each previous innovation is a step up on the ladder of development, quality work that you can incorporate and increase the impact. But as you get further on the right-hand side, you're naturally building on a lot more previous innovations, and it's harder for you to be novel. So this tension gives you this inverted U shape between these two measures. Now, combine that with the second fact, which is that teams are building on more and more prior work. So here I'm showing in this figure the average team field density for new teams in each year. So the field density is given by the quantity of previous innovations the team is building on divided by the volume. Okay, so the volume is essentially a measure for the size. In the simple context of the line, it would be the length of the line. So it's the number of patents the team's building on divided by the length. And I'm showing you here that teams over time have much more crowded knowledge fields. They're building on denser research areas. And you might be concerned that this is a mechanical outcome, okay? Because you fix the space, so over time, density must go up. But it's not necessarily the case. One, I'm only showing you for new teams. So this is only the first time the team patents and never again. And the team could endogenously be locating themselves on top of new areas where there's no previous innovations. So it could be flat at 0, but it's not. We see it's increasing as teams have an inertia to build on what came before them. Then the size of the point is weighted by the number of patents. We all know that there's been an explosion in innovation. So teams are building on more prior work. They have an inertia to build on what came before them. So this is why I argue this is a micro representation of the fact that ideas are getting harder to find and why teams are increasingly on the downward slope of this inverted U shape. They're building on a lot of prior work, and this will affect their ability to produce a breakthrough. So these two facts combine to explain the first empirical result. And that is, given the average treatment without replacement, which means that I can take, on average, how many patents are removed before the inventor is replaced, and it's around 175. A team's breakthrough chances increased by 22%. And I get this coefficient using the measure in the table, where the first row is giving us prior work. This is the quantity of previous innovations within the team knowledge field, where this is negative and significant, precisely because teams are building on lots of prior work. They're increasingly on the downward slope of this inverted U, so by adding more, you're going to reduce the chances that their patent becomes a breakthrough. The treatment, which is the D, the middle row, essentially reverses this. By shifting the team into less explored areas of the knowledge space, you increase the chances that their patent is a breakthrough on average. Okay, so this does not mean, though, that team managers should take this as a golden rule and go on a quest for novelty, remove team members from more established fields. Okay, even though it's conditional on the volume, the fixed effects, etc., it's hiding significant heterogeneity, which I will show by splitting the sample by the first measure, prior work, and comparing what's the effect of decreasing the quantity of prior innovations a team is building on for a team building on an advanced area with a lot of previous innovations and those building on only a little. So in the graph here, I've split up prior count into 4 quartiles. So Q1, a team's building on relatively little, and Q4, a team's building on relatively a lot of previous innovations. And then I run the regression again 4 times. And I'm plotting the coefficient, which in this case is positive and significant for each of the 4 groups on the treatment of reducing the quantity of innovations they're building on. And we see that for teams building on advanced, well-developed research areas, it doubles. So it's very important for those teams to increase their novelty. So to reduce the quantity of previous innovations they're building on, push them into less explored areas, allows them to be more novel and create more breakthroughs. However, for teams in the early stage research areas, and we might be interested in those in particular, given they could be startups or spin-offs, etc., the same change of reducing the quantity of prior innovations that they're building on harms their chances of a breakthrough. And I'm going to show you now in the final slide supportive evidence to say that they are in fact on the upward sloping region of this inverted U shape. And they would do better by incorporating more established knowledge. So I want you to compare this graph, where we have the quartiles of prior work from Q1 to Q4, to the following one, where here I'm merging in data from Sam Arts and co-authors, and in their paper, they counted the number of new vocabulary, so new words or new bigrams or trigrams, where a bigram is a combination of 2 existing words. For example, artificial intelligence, they would measure the first paper to use this, or patent, sorry. And I'm going to take their measure as a measure of novelty. Are you introducing new vocabulary? And run the same regression, but with this new outcome measure. So that's why I have 3 points. And I show in this figure supportive evidence for the previous result. For teams building on advanced research areas, reducing the quantity of prior innovations, which again, here I'm plotting the coefficient on this treatment variable D, reducing the quantity of prior innovations that a team is building on, increases their creation of new words and new combinations of words. So these teams in advanced research areas are being more novel. Okay, so a breakthrough requires increasing novelty or increasing impact. So these people are building on a lot of prior work, they're being more novel, therefore creating more breakthroughs. But almost most interestingly is the teams in the early stage research area, where we saw that there was a decrease in their chances of a breakthrough by reducing the quantity of prior work. We see that their novelty remains statistically the same. They are not being more or less novel. So by holding novelty constant, I argue that their impact must be decreasing to explain this drop in the chances that their patent goes on to become a breakthrough. So these teams, in fact, would potentially do better by increasing the number of previous innovations that they're building on, allowing them to create more breakthrough innovations. So just to conclude for the final minute, because I don't want to take too much of your time, this novel framework allows me for a latent representation of the team in data. And I use this high dimensional pattern text data to back out this measure of breakthroughs, but also model teams that allow me to make alternative policy recommendations that I mentioned at the beginning. These exploratory R&D funding we know needs to be novel and push into new spaces. However, this inverted U shape suggests that there's a limit to how far it can go. And this paper then suggests that cross-field collaboration might be a way out of this problem. By combining inventors from established, well-developed fields from those from early up-and-coming fields, the inventors from early fields can act as a novel perspective or as a wild card to present and create more breakthroughs in combination with the advanced field inventors. So combining the two, potentially through NSF, ERC projects, we might be able to drive the creation of breakthroughs. And we care about breakthroughs precisely because they are new and successful research fields. And this framework, thanks to the use of high-dimensional data, is precisely suited to studying this type of innovation. So hopefully there can be a further study of this potential policy outcome, maybe using more of a modeling approach. Okay, so I'll finish there. And thank you very much for your time and listening.
Thank you, Joseph, for the very impressive presentation, methodologically extremely innovative and advanced. But I'm handing over to Ernest for providing his comments and remarks to the current state of the study, I would say. It's an ongoing work, right?
Yeah, yes. I mean, I've just gone through the job market with it. So now I've got a lot of feedback from the job market that I can work on.
Okay. So Ernest, the floor is yours.
So can you see the screen?
Yes, great. You do not have it in presentation mode, but I think it's sufficient for now. It's
how do
I think it's sufficient.
Does it work now?
Yes, perfect.
Okay, so first of all, let me thank you, Joseph, for this nice presentation. I agree with Thomas that yours is a great methodological contribution. I love working with patent data, and I really liked what you did. And even though I'm, let's say, lagging behind a bit in these methodologies of text analysis of patent data and also scientific data, I would like to catch up because I find it fascinating. Just a recap that my name is Ernest Miguelez from the University of Barcelona, and I also kind of retained my previous affiliation because I just arrived to the University of Barcelona like 1 month ago. Before I was at the Institute of Public Policy of the CSIC, the Spanish Research Council for a year, and I spent also 10 years of my life working at the Bordeaux School of Economics in France. So my discussion is, I try to recap a bit what I understood of Joseph's paper, and particularly, although he explained it very well, so I go fast through it. I want to highlight the strong points or contributions, or at least the ones that I like the most. And then I will list the things that I missed, or to say it better, that I misunderstood. So, and feel free to pick the ones you want to reply, or maybe we can keep talking later on and so on, because it's a long list plus some of the things clearly you clarified during your presentations. Just to recap, Joseph's papers wants to study the impact of expanding the technological frontier on teams' innovation, particularly the effect of the prior knowledge of the teams on the probability of producing a breakthrough patent. It uses a lot of text analysis and natural language processing. The main result is that teams produce more breakthrough patents when they build on prior knowledge, but not too much that it becomes too hard to be novel, right? Which is actually is not a new finding, but especially from the literature I come from, and I will come back to it in a moment. And Thomas, I'm sure, agrees with me. But it's nice to put it in at the individual and team level. Also, the results that teams work in advanced areas for those teams, losing a team member fosters the potential of a breakthrough pattern, while those working in early stage fields suffer more from removing key members of the team. This is the last result we saw. Point that I like a lot, the new measure of a breakthrough pattern, which I see some issues to be discussed, but I see a lot of potential there. Of course, as I mentioned before, the text analysis to define the knowledge areas or knowledge classes. I love this idea of trying to measure what is the contribution of each of the team members to the new pattern, which means that quantitatively speaking, like the shares of the contribution, but also the topics of the contribution, right? And this is you did great examples out of it. Of course, the use of the collaboration that again is not an innovation, but it's a good use of it, and it has not been used that much. I agree that a deeper understanding, and this is a sentence of Joseph himself at the end, a deeper understanding of the determinants of breakthrough patterns is very important, because only a tiny percentage of patterns are actually, it has been shown that are actually relevant for the economy. So understanding these tiny percentages is important. And I agree too that the paper marks the beginning of a rich future research agenda in which to study team dynamics and innovation. That's cool. So things that I missed or possibly I misunderstood. So the first issues with respect to breakthrough patterns, which again I like the idea of making it sort of a more endogenous to the research area, let's say, and not using either new classes or forward citations. That it has been the norm in the related literature. I had not sure from where it comes from, but I had always the feeling that there was some, and I think that you mentioned it in the presentation, that there was some sort of mechanical correlation between the idea of being a breakthrough pattern and yes, having some work done before that moment T of the application of that pattern and the growth afterwards. I saw some sort of mechanical correlation with the inverted U relationship. I also like the robustness you provide using other measures of breakthrough patterns, including forward citations, if I'm not mistaken. I would have loved also to see that in regressions, not only correlations in the data. That's a suggestion, maybe. I was wondering whether knowledge areas can have more than one breakthrough patterns, which I guess yes, but this was not clear to me. I was also wondering whether to know more about the breakthrough patterns, particularly the distributions of these breakthrough patterns, the one you found across technological fields. And when I say technological fields, I'm thinking about the predefined technological fields, either 5 big areas or 35 smaller areas, something like that. What I'm saying that, because if I understood well, there is no, so you assume that the rate of growth to be considered a breakthrough is kind of homogeneous across different areas, right? And I was wondering whether there might be some areas in where patenting, or they might have had like processes of patenting, big patenting, and this ends up with several breakthroughs in that area, while others, the growth was not that big compared to the biotechnology, but still it was kind of big for the field, right? So I was wondering whether this, in regressions or even in the way you compute breakthrough patterns, you control for the timing, and this is very important. But I was wondering whether it might be important also to control for differences across technological fields. I also have a question about machine learning. Also, it's not I'm kind of being introduced to that by force lately. So I was wondering why using only a part of the USPTO for the model, only 400K patents, 200K invent teams, if I'm not wrong. If the model is already unsupervised, why not using the whole thing? And this comes from my ignorance out of it. So I've worked with supervised models in where I have an annotated sample, and this is super clear to me. For unsupervised models, it is not clear to me why you need to split the samples. A reminder that patents are not scientific articles. Even at some point in your paper, you said solo author paper when you were referring to patents. This is important for the writing of the paper, of course, but it is also important because how patents are written, right? And I mean, I've talked to several inventors in my personal and familiar family network, and they never write the patent themselves, right? So sometimes, I'm not saying that always others do it, but many firms have like the specific people that is specialized on that. Sometimes it's the attorney in the US Patent Office data, and you show that you have the name of the attorney or the firm who does that job. So I was wondering whether this could affect especially the contribution of each inventor, and whether at least this should be acknowledged. You know, that this is the complaint I always have with people working in patent data, that we believe that inventors are like us scientists, and it's not kind of the case, right? So we need to have this into account all the time. Which brings me to the examiner too. I was wondering which drafting you used, because you know, the patent text and the claims of the patents can change a lot during the examination process. And there was one paper published in RISTAT in 2012 that was showing that there is sometimes even callings between applicants and inventors and the examiners. And the resulting pattern change a lot. So again, I was wondering whether this maybe should be mentioned somewhere. You call it knowledge classes, which is great, but at some point I had the confusion with patent classes, which you don't use. So why introducing this confusion and maybe finding a better branding of what you do, right? I was also wondering how many knowledge classes you end up having. And I was wondering whether these knowledge classes are constant over time, whether they merge, they are split, you have engines, and engine is a knowledge class or knowledge area, but eventually your algorithm may say that no, now it's not engines anymore, but electric engines or whatever, I don't know. So I was wondering whether you could say something about that. I had also problems to understand how the team is defined, actually, because when I start reading, I don't know, I'm not sure, you tell me. I kind of understood that the teams, so you were using like the text analysis to define the team, right? And that I found very exciting. But then I realized that maybe that was not the case, that you were using a more classical definition of team, which is like having invented together, which is, of course, easy to understand and it's easier to deal with. But then I wonder how many times teams patent more than once, right? And what I missed in the paper is some more descriptive analysis. Is the team size, patents per teams, team composition over time, team changes. You mentioned that the team can lose a member because of the death, and this is used for exogenous variation. But teams can evolve in many ways over time, right? So for instance, in a paper, one of the paper you cite of myself, what we do is that we define a team leader, right? And we don't follow teams over time. We follow leaders over time. But maybe one way would be to define a sort of a team leader of an idea, of a concept, and how his team evolves over time, and how, you know, he's the incumbent, and you may have newcomers and collaborators that die, and so on and so forth. But to have something more homogeneous over time. Why I'm saying this then, because I look at USPTO data and actually find that so many, the majority of inventors in the USPTO and other offices too produce only one patent. It's the production of a big number of patents is very skewed. Team size is also very skewed. This is something that we know, right? If you are using those teams that, you know, have some continuation over time as if it was a research team, I'm wondering to what extent you are looking at the very end of the talent distribution or the skill distribution, right? So this is something I would have loved to see some more discussion about that, as well as some description of the data. One thing I missed, and also this because this is from where I come from, is some relation to the literature that I have also mentioned, all the vocabulary that I have used here, like knowledge space, technological lock-in, path dependency, novelty, breakthrough patterns, and relatedness. And I'm citing some of the authors, and I'm sure that Thomas agrees with me. There is this principle of relatedness that says that countries that you can adapt to teams, and that would be great, move to new knowledge areas if they are related to their current portfolio, right? And this brings me to another idea that maybe is an idea for another paper, that you look at whether the team has previous experience, but I was also wondering whether you can somehow introduce the idea of not previous experience in that same knowledge, but the related knowledge versus unrelated knowledge. And there is some work precisely on breakthrough patterns and related versus unrelated knowledge, not at the level of the teams. And I think this is a great contribution of your paper at more aggregated level. But why not looking at that, or why not maybe for future work exploring that? Also, I know that you put some firm controls, particularly the size. I also miss a lot of the idea of the role of the organization and the role of the cluster. Again, inventors are not scientists. Inventors work, also scientists work in organizations, but organizations like firms are very hierarchical, and oftentimes the inventor has no power on the decision on with whom to work and the topic he works about or she works about. So it's important at least to acknowledge that and maybe try to do something about that. I know, again, that you put these controls at the firm. There is a long literature on clustering and the role of space and knowledge diffusion, and I'm sure that the chances to get a breakthrough pattern or the evolution of the knowledge area itself is very different in Silicon Valley than in the middle of nowhere, right? So I think it's important to acknowledge. And following up with the geography idea, you didn't mention nothing about inventors moving around, and therefore also changing the distribution of teams, or maybe not changing the distribution of teams, but him working in another place, which also can change his or her knowledge portfolio. You didn't say whether patents are like, of course they are teams, and they are collaborative patents, but you didn't say whether they are local teams or international teams, things like that. Some word on that would be nice. acknowledgement of that. I assume, because you mentioned that your sample is from 1990 to 2011, which is, although you don't say any reason about that, but at least you mention it. You don't mention whether your inventors are from the US or from elsewhere. You use I guess that you're using the whole USPTO, but you don't say anything about that. And for me, that I come also from from geography, this is a bit shocking, but I guess this is adding 2 words. I looked up the patent US 6166-211, and I got a different title than you got. It was sequential benzylic oxidations of the naloxone ring system. So I don't know if I did it wrong or something. And I also had a final question about this idea of that you do this classification of when teams lose a co-inventor because of he or she dies, whether they substitute him, her, or not. I was wondering whether they can, for instance, for a while not substitute him, and after a while they substitute him. So I was wondering, these teams, where do you classify these teams? And I think that's all. And again, thank you so much for the great paper and the great presentation. And of course, feel free to answer the questions you pick, and don't feel obliged to answer everything, because otherwise it will take.
Thanks, Ernest, for the very extensive comments and very useful. I guess you should provide Joseph with the slides, because there are so many useful and valuable remarks to it, methodological questions, but also ideas for future research. For it, of course, I personally would very much be in favor of going more into the geographical discussion that Ernest has brought up. Not only in terms of clustering, but also in terms of what's the geographical spread or distribution of the teams, and how this is affecting the probability for breakthrough, because there are a little bit contradicting hypotheses in that direction. One group says if the geographical spread is higher, that the knowledge gain is also higher, and therefore the probability for breakthrough is higher. Others say breakthrough even more needs the exchange of tacit knowledge, and therefore geographical clustering should be higher. So maybe with your approach you can test it. Joseph, you may want to react. I would suggest that you cluster some points of that Ernest mentions, otherwise it becomes too extensive. So I hand back to you.
Perfect. No, thank you. Thank you so much, Thomas and Ernest. Honestly, the value of this type of discussion cannot be understated, right? Like we all know, to get someone to read and give that feedback is wonderful. So I definitely will take you up on your offer of coffee to go through some of the points, because I won't respond to them all, but yeah, I'll cluster them a little bit, like you said, Thomas. So some of the questions were around maybe how I classify teams and what I think about a team, and then the shock of the death to the team. So I do use the kind of more typical method of, if I observe the names together on a patent, then I call that the team. However, I allow for small changes, and I call them the same team. And the 2 small changes I allow is to remove a deceased inventor, or to replace a deceased inventor with one other inventor, right? So the idea is, I thought, and I still think, that if you observe like 4 people patenting together and then you remove one of them, calling that a brand new team seemed too strong. So I was trying to use an idea of allowing for small changes to then allow me to observe these teams over time. Now, this links to your idea of how often do I see these teams and these inventors. So it's true, a lot of inventors, I mean, your data was perfect. Yeah, a lot of inventors only appear once. And I will be, by looking at teams that repeatedly patent, one concern is that I'm looking at the more successful teams, right? I think that's a very valid concern that I need to think about, if this means that there's going to be some kind of bias in the result, given that I will be observing potentially a team, for example, like 4 people together 1, 2, 3, 4, 5 times, because the average number of patents that I see them produce together is around 5. So these are highly frequent teams. So your query is completely valid. And just to mention on the sample, that's probably just a mistake of mine, especially today in the presentation, of not explaining well the sample years and going too quickly. And it links a little bit to your point on training versus fitting. Why do you have this unsupervised data? So I'll transition into that with this link of, I estimate the knowledge space from 1976 until today, okay, until 2022, I think. And within that sample, I use 1990 to 2011 only for the regression sample. Why do I do this? In my mind, what I need to do is locate these inventors on these treated teams and these controls that I want to use in this regression in the global knowledge space. So for example, the teams at the beginning, I want to know how much prior work are they building on. For example, the team in 1990, if I was to start the knowledge space then, I would be unnecessarily left coding these teams. And so I go all the way back to 1976 to get an idea of how much prior work they were building up. And the same goes for the teams in 2011. By running it forward, that gives me like 10 years afterwards to still get an idea of how much prior work built on their own. So that was a mistake of the presentation. It's 1976, 2022, and then the subsample for the regression. And your question about training versus fitting is a very good question, a very astute question, and it's simply due to computational limits. So I was running this locally on my laptop, and I didn't have a state, because it takes a very long time to run. I didn't have a stable place to run this. And the idea then is to train it on a smaller sample that represents the distribution of technology that I want. And then once you've learned, and included in that sample are all the teams in the regression and more, okay? But all the teams in the regression, so that I can count how much prior work they were building on, disentangle the contribution of each team member, do all the key mechanisms. But then once you've learned the knowledge classes, you've learned these fields, you can represent any text you want in the same space. So then I draw another 2 million patents to populate that space using those learned knowledge classes. Why? Because this allows me to get this global measure. So what happened before, what happened after, etc. And the only reason I could have done it by putting the 2 million texts in at once, but my computer would have complained, right? That's the only reason why. So as long as you buy that they are both representative samples, then it's fine. But ideally, once I get some computational power, I'll just run it on the whole sample. And then linking to that, mentioning the topics, so for me, the topics, I use 50 topics. So it's not a line, it's a 49-dimensional simplex. Now, the number 50 is ad hoc. I've run it with 100, 225. It doesn't change much apart from it becomes more coarse or fine, the classes. There's no way of splitting them, like you mentioned in your class, like each one is separate. In some ways, it doesn't really matter. Right? Even with a one-dimensional line, in theory, you could run the same model because you'd have to just change the radius. So if you remember this radius that I draw around the patents or around the teams, by making that very, very small, you could then work in a very small dimensional space because it's all about the relative location of patents within this bigger location. So it doesn't actually matter too much. It more matters on how well you want to represent the knowledge within the patent texts. Okay, so that's a kind of very light answer to that question, where just to then summarize the rest of the answers is I totally agree that targeting more of the geography would be an interesting idea. So I don't use any information on location. I don't use it. So it will include teams that are combining inventors from very far distances. They could even have international inventor teams. And this will be a relative control. So one, it should just be a relative control. Let's say if the inventor living in Japan is the one that passes away and we replace them with one in the US, this matters. But even beyond that, merging my kind of technology knowledge space into a geographical space would be a very interesting way of doing so. For example, correlating the distance in my space with the distance in a physical space would be a straightforward way of mapping these clusters into my location. So at the moment, I'm not doing anything along that avenue, and I agree 100% that it's an obvious kind of elephant in the room, because you're right. I'm using a lot of the language, but I'm not tackling any of the related concerns. So I think I cleared up maybe some of the more obvious points, and then maybe some of the deeper questions, maybe about whether I'm using the right classification, or if I've missed any small things, maybe we can talk about them further, or we can jump into the discussion now if you like. I'm not sure which is best.
I think we could jump into the discussion for now. But probably many issues have already been raised. So I'm asking to the audience if there are other comments and remarks from your side that Ernest didn't mention, which is almost impossible. But I see one question from Gigi. Hello.
Hello.
Hey.
Thank you very much for the very inspiring job market paper. I'm very impressed. I'm a newly postdoc in a technology university in Germany, and I'm mostly working on scientific papers, and so not patent. And I'm also new to this NLP approach, but I worked on a similar approach in order to classify whether a paper belongs to a theoretical paper or an empirical paper. And that way, we also trained a probit model, some kind of algorithm to classify the papers. But in the end, when we try to put a small sample and compare with a manual classification, there's still some significant difference. That's why the whole process of paper got slowed down, because we decided to discard the model. So I would like to ask you whether you test your preciseness with the manual sampling.
Great. In terms of the knowledge classes, yes, this is one thing that I can link to a previous point, was we compared the breakthrough classification, but that's slightly different to what you're asking. In terms of the knowledge contained in the patents, not as directly as cars to cars and mobile phones to mobile phones, but we did do something that I think goes back to one of Ernest's points, which is we first of all showed that the knowledge content of the team's patents changes after the death of an inventor. And this kind of speaks to the concern that it's only the firms directing innovation, and it's not the inventor teams, because we show, for example, instead of classifying breakthroughs, patents as breakthroughs, we classify them given exogenous measures of knowledge content. So we use three. We use, is it a green patent? Is it an automation patent? Or is it a cancer treatment patent? So these kind of three groups that we take from other data, either from technology classes or other papers. And then we show that there's no non-linearities, or there's no non-monotonic relationship between, as we see with this inverted U, with the quantity of previous innovations of a given type on the probability that you patent in that type. So for example, we show if for every additional patent within a patent's research field that's green, that patent is more likely to be green, okay? Which is straightforward, you're just spotting that it's clustering by types, by knowledge content. But also for every patent removed from a team's knowledge field that is green, the probability that their next patent is green goes down. Okay, so if you lose the green inventor, you're going to lose your ability to produce green innovations. So in terms of manually checking, it's not the same. We're not taking, we're not saying that this patent is green, like we can't do any cross-reference table or anything like this. But in terms of the kind of message of the paper and the fact that we're capturing the knowledge direction of the team's, innovation, there I think this is a reasonable check to say, one, the death or the type of innovation you're creating changes as you move around this space. And therefore, then we link it to the second step. So I think in terms of manual stuff, maybe we could do a little bit more, but yeah, I hope that clarifies what we do and what we don't do.
Yeah. And another small question is just for my own information. What kind of data you use to get the information of the death, the scholars?
So that's a paper by Kaltenberg, Jaff, and Lachman. So this is, I can send it if you want. where they use these American, it's US data. So in that sense, I won't be using too many international teams, given that I use this data. And I think this is, I'm 99% sure it's only US, where they scrape these online registries. And so they get the birth and the death date of a huge percentage of the US PTO inventors. I remember exactly what it is. And they give you the birth and death date. Now, this is messy data, right? So sometimes you'll have many birth dates, many deaths, but you can kind of filter out the more accurate ones. So it's directly from them. It's
Okay.
not.
Yeah, thanks a lot. Thanks a lot.
Thank you. Thank you very much for your question.
Further remarks, questions, comments? Maybe one final from my side, Joseph. So one of the aspects also Ernest touched is, I mean, you may have a question of all kinds of robustness checks when you publish this in comparison to other models or in comparison to other indicators. And the most obvious question one reviewer may raise is that, why do you need such a huge effort in creating your knowledge base when you may get the same results with the detailed EPC classes that you have going down to 6 digits, 7, or I think even 8 digit meanwhile? Is there something you could react to it, or do you think that you get different results than when you take the predefined classes? Because as you know, the patent offices are putting really a lot in a very detailed and very dynamic classification of technological space.
For sure. For sure. No, my strongest concept of this is that at the patent level, the technology classes do a fantastic job, right? Especially the lower ones that you're describing. But they are not so good at describing the inventor level, given that you cannot disentangle, I think, correct me if I'm wrong,
Yes,
but the
okay.
number of classes would be like 4 or 5, maybe.
Okay.
This is not enough variation to know what you did compared to what I did, where you use words in the patent to be able to get this variation. So you can aggregate up, right? A typical method would be like, if you and I produce a patent with 5 classes, then we both get these 5 classes, right? This is a decent way, but this allows for no concept of collaboration or academic division of labor or scientific division of labor. So that's where I think that the reference comes. It's not better at representing patent level knowledge. It's that's
okay. Thank you.
Thank you all. Thank you very much.
So if there are no other questions, thanks again, Joseph, for the very impressive presentation. Thanks, Ernest, for the very extensive comments, very useful, and also for the audience. I'm asking Georg to blend in the slide of the upcoming seminar, which will be a colleague well known also from the RISIS community of the Max Planck Institute, Ali Akbaritaba, and he will talk about differentiating emigration from return migration in digital trace data, a case study of scholarly migration. And this will be discussed by Nicolas Robinson Garcia from the University of Granada.
Perfect.
So we are looking forward to seeing you again in the next seminar, and have a nice day and a nice remaining week. Thanks, Joseph, Ernest especially. Goodbye.
Thank you.